Today we're going to be talking about right triangles and similarity in right triangles. We talked about similarity before break, and so we're going to be working back with that idea of similar figures. Our first theorem, our only theorem for today, says if the altitude is drawn to the hypotenuse of a right triangle. So we're going to start by drawing ourselves a picture here. But think about what some of these words mean. So altitude, what's another word for altitude? Height. When you get your height measured, so when you go to the doctor's office and they want to measure your height, you have to stand straight up, right? You can't like tilt. They wouldn't want you to do that. They would tell you to stand up straight. When you stand up straight, you are standing up perpendicular to the ground, right? Your feet and your legs are making a right angle with the ground when you stand up straight. So when we draw an altitude in a picture, we're thinking about perpendiculars then. So it says it's drawn to the hypotenuse of a right triangle. So what we're going to do is draw a right triangle, and we want to draw an altitude or perpendicular to the hypotenuse. Which side of the right triangle is the hypotenuse? The longest side, or the side across from the right angle. So what I'm going to do is go from the right angle across to that hypotenuse at a perpendicular angle. When I do that, I now have three right triangles in this picture. I have the original big right triangle, and then when I drew that extra line into it, it made two more right triangles. So there are three right triangles in this picture now. It says if you draw a picture like this, then the two triangles formed are similar to the original, the big one, and to each other. So all three of these triangles are similar to each other. The type of similarity, if we were going to prove this, which we're not, would be by an angle-angle similarity. So we talked about angle-angle similarity back in chapter 7. When we studied similar triangles, we said we could then set up proportions to solve for certain pieces. So from those three triangles, we could set up some proportions to solve for missing pieces. And that's what these corollaries talk about. It gives us some formulas. So instead of setting up all the proportions and solving it, we're going to take the formulas from these corollaries. The picture and the formulas that I'm about ready to draw are super important to your homework tonight and to getting ready for the test. So I would strongly suggest that you copy down these pictures and formulas. So we're going to draw the same picture we did last time, except I'm going to draw it on its side so that the hypotenuse of the big triangle is the side that is kind of laying on there. Then, like we did in the last time, we're going to draw in an altitude or a height perpendicular to that hypotenuse. Now I'm going to label the pieces of this picture A, B, C, D, and E for the segments that are formed. So the first corollary says, when we draw this picture, the length of the altitude, well, the altitude, using the letters that I labeled there, the altitude would be C. The length of the altitude is, or equals to, the square root of the product. What does product mean? If I take the product of two numbers, what am I doing with them? Multiplying them. So we're going to multiply. So the product of the segments of the hypotenuse, that means the broken pieces there of the hypotenuse, so that would be A and B. So that first corollary tells us that C is equal to the square root of AB. It also then defines for us what geometric mean is. When we ask for the geometric mean of two numbers, what we're going to do is take the square root of their product. Okay, so some of your homework problems will ask you to find the geometric mean of two numbers. Take the square root of their product. The second corollary says, when we draw this picture, each leg, and that means the legs of the original one, so like D is a leg, is equal to the geometric mean, so that means square root of the product, of the hypotenuse. That means that whole original hypotenuse. So that would be A plus B, that whole bottom piece. And the segment of the hypotenuse, or the broken piece, that is adjacent or close to it. So what part is close to D that's on that hypotenuse? So on the original triangle hypotenuse, which piece is close to D? A. And likewise for the other side, E is equal to the square root of the whole base times B, the part that's close to it. This picture and these three formulas are going to be crucial for your homework and then also as we go into the test. So make sure you have that copied down. Great, in this picture, on the top, we have that same picture we've been drawing where we have the big right triangle breaking it up into two smaller right triangles. If the measure of angle R, down at the bottom corner here, is 30, how big is RSU? So that would be this piece. R's
70?
Close.
Do you have to write down all these things?
As much as you want. I mean, these are your notes. I'm not going to check them, so it's not 90.
Oh, wow.
It's 60. How do we get 60?
You add 30 and a 90.
Yep, we've got a 90 there. We've got a 30 plus 60 would give us 180 and make a triangle. So then the next blank, how big is TSU, which is the one that's right next to that 60? 30, because all together they make a 90 in that corner. And lastly, how big is angle T up at the top? 60. Because in this whole big triangle then, I have a 90 down in the corner at S, 30, and a 60 then up by T. So according to angle-angle similarity that we talked about before, we've got a lot of angles matching up here, so that means we have some similar triangles. So we're going to name them. Remember when we name them, the order of the letters is not random. It determines the relationship. So the first one we're going to call RST. That's the whole big triangle. Let's name the bottom one first. Angle R in the whole big triangle is how big? 30. What angle in the bottom triangle is 30? Still R. So we'll start our name with that. In the whole big triangle, how big is the angle at S? The whole triangle. 90. So which angle in the bottom triangle is 90? The one by U. And then since we're naming the bottom triangle, what other letter do I need? S. Now let's name the top triangle. Again, I'm going to compare to the whole big triangle. So R was 30. What's 30 in the top triangle? S. In the big triangle, S was 90. What's 90 in the top triangle? U. And what other letter do I need for the top triangle? T. So we have some similar triangles there from angle-angle similarity. Okay, geometric mean. How do I define geometric mean? So if you want to find the geometric mean between two numbers, what do? Square root of product. So what is the geometric mean of 2 and 3? The square root of the product. 6. 2 and 6. Square root of product. 12. Simplify square roots when possible. We learned how to simplify square roots yesterday. What's a perfect square?
3. No.
4 and 3. And what's the square root of 4? 2. Square root of 3 is ugly, so it sticks around. Simplifying square roots like we did yesterday. Every square root you give as an answer should be simplified, even if the directions don't specifically say so. We always want to simplify our answers. 4 and 25, square root of product. 100. What is the square root of 100? 10.